Hello, welcome back to day 85. So we've done 85 days so far. I have done 85 days so far on this stream. So yeah, it's been an amazing journey, and we're heading towards the end. And prepare for more challenges in the future. Anyways, how are you guys doing? I know nobody's in the stream right now. Well, anyways, I'd like to welcome you. In case you're watching in the future, um, nice to have you here in the stream. Today we are going to be looking at a few questions, um, a few data structures and algorithm questions. We'll have um, we'll have to solve some question I started yesterday. I'm going to solve some question I started yesterday, and also I'll be revising some other questions as well. So I took so today is going to be a mix between two data structures, trees and linked lists. So we'll be having a look at those, and also maybe when there is time towards the end of the session, I'll provide some resources to learn about trees. In fact, I already have them linked in the description of this video, so you can take a look at that. Alright, let's see if there is anybody in the chat. So I'd like to refresh. Um, okay, so Ransom is here. Always punctual. Nice to have you here, Ransom. Good evening. Um, yeah, I stream every day. I can't miss a day until I'm done with the 100 days, right? It's a challenge that I set for myself, so I'm making sure I complete it. Okay, so we are going to go through some questions from yesterday. Yesterday, I solved a question on. Let me see. Well, I didn't. Okay, so here's a question I started yesterday. Um, I'll check the questions from yesterday and see which ones. Um, okay, so I did search in a binary tree. We search for a value in a binary tree, and also I also did. So yeah, this was the question I couldn't finish yesterday. Range sum of binary search tree, right? I actually solved this question today, earlier today. So let me show you. I was just trying to revise for the stream, so I managed to solve the question, and I'll be sharing with you how I did it. Where is it now? We have, it will be this, right? Branch is the question here. So you can see, yeah, so you can see I solved this not long ago. About an hour ago, yes. So about an hour ago, I solved this question, and I'll be sharing the solution with you guys, and also, um, some steps into or techniques to solve this question as well. Um, so let's see. Any questions in the chat? No. Before I start, yes, it'll be left with two. It's left with 2 weeks, right? Yeah, 2 weeks. I think. Let's see. Mm, so we end on. So 5 days from now we'll be here. So that will be 90 days, and the next 90 days will be here. So around 27th. Yes. So, oh, nice, nice. The random module for getting random integers, right? Yes, so you can use random to get random integers. So, uh, somebody said, why are you doing DSA with Python and not CSS or C++ or Java? Well, I don't code in those languages. I mean, there is really no requirement for a programming language for you to solve DSA questions. You can use any language you want. So since I'm familiar with Python, I went with Python. Yeah. Do you code in C++? And have you been doing any data structures and algorithm questions? Okay, so let's get started. I would like to read the question and we'll go through it step by step. So here is we'll first of all start with a tree question, which is searching a value in a tree. So binary search in a tree, and we'll see how that is done. I have a tree here. I will erase everything on the screen now, and we will draw this tree over again. So I'll take this tree and put it here. Now, let's read the question. The question says you are given the root of a binary search tree, BST, and an integer value or val. Find the node in the BST, which is the binary search tree, that the node's value equals val, and return the subrooted tree, the subtree rooted with that node. Okay, so find the node. Let me read this again. Find the node in the BST that the node's value equals val, and return the subtree rooted with that node. If such a node does not exist, return null. So the idea is for us to search for a value in a binary search tree, right? And with the way a binary search tree is structured, I mean, understanding the structure of a binary search tree, that will help us solve this question. At least to give us a head start on how to quickly find a solution for this question. So first of all, we need to understand what a binary search tree is. So let me come here. Okay, let me use this image, right? So a binary search tree is a tree or is a data structure that is made up of nodes, and the nodes are connected in a tree-like structure. So in a binary tree, a binary search tree, or in a tree, we have the first node in the tree, right? So every value, every all of these circles you see here are called nodes. So we have nodes in a tree, and each node has a particular property, right? And they are all similar in terms of their property, right? So here is how a node in a tree is structured. So the node has a value, right? Or you know what, let's use this. The node has a value, so I'll put this. In this case, the value of this node is 2, so I'll put value here. And the node has a right and left child. So this is the left child of this node. So left, sorry, let's do it this way. Left and right. Now you can see I didn't point directly to this node here. The reason why I pointed to this line instead of pointing at 1 is because even though 1 is still a child of this node 2 here, in a normal form, the node will not have a next child, right? So in a normal structure, the node would look like this. We'll have, let me do it this way. We'll have a value, and the value is what we insert into the node when we are instantiating the node class, or when we are creating an instance of the node class. So this is where our value will go. I'll call this val, and then we'll have a right and a left, right? Initially set to none or null in the case of your programming language. I'll just use null here. So this is what a node in a tree looks like in its normal form, right? Or in its let's say normal state. Sorry, my network just went off. I hope I am not uh, totally disconnected from the chat. I'm so sorry. My internet just got disconnected. So sorry about that. We have bad network over here, so I needed to like check again if I'm still streaming live. Okay, I'm still live, which is good. All right. There are a couple of questions here. I can see somebody said 2,000 plus rating on Leads Code in 6 months. Possible. I'm a beginner. Well, yeah, you can. I mean, I would say you shouldn't focus on the ratings. Just try and get better at solving the questions, right? So that's the only thing you need. Das said, first get your basics strong. Yes. So exactly. Yeah, nice to have you here, Das. Thank you very much for coming to the channel. This is nice. Okay, so let's get back to the explanation. I would quickly recap. So I was explaining the structure of a node in a tree. So the node has certain properties, right? We have a value, and we have the right and left child. You can call them right and left. But the right terminology is to use is the right and left child. Now, the left nodes are inserted in a tree in a specific manner, right? So, what do I mean by that? Well, with the way a tree is structured, from the root node, so the first node you see in the tree is called the root node, right? So, from the root node, we begin to determine where exactly a particular node has to go to, right? Or in which direction a particular node has to go to. So in the case of 2 and 7, right, if you observe this tree very well, you will see every value to the left of the root node is less than the root node, and every value to the right of the root node is superior to the root node's value. So which means, so to the left of every node in the tree, be it a root node, right, or a child of the root, or any other children in the subtree, the left values or the left subtree will contain values less than the parent root or the root node, right? And the right subtree will contain values superior to the root value, or to the parent node. So in this case, 2 is the parent of 1 and 3. So you can see 3 is superior to 2, right? So 3 goes to the right of 2. And in the case where 1 is less than 2, 1 goes to the right of 2, to the left of 2. So 1 is the left child of 2, and 1 appears in the left subtree of the root node. So this entire thing is called a tree, right? And this portion here, from here all the way down, and if there were other nodes here, they are called subtrees, right? So this is the left subtree of the root node, and this is the left subtree of this parent node here. And the same thing applies to the right subtree as well. So anytime we want to insert a value in a tree, we insert them based on, we make a comparison, right? So if the current node we are trying to insert in the tree, let's say we want to insert, I'll erase all of these things. Let's say we want to insert, a an 8, right? An 8 into this tree. So what we will do first of all is to traverse the tree up to a point where the condition is okay for us to insert that node in the tree. So since we have our node here, this is 8, the node has a value of 8, then we'll first of all compare the value of that node to the root node, because the beginning of our tree starts from the root, right? So we compare it to the root node and determine in which direction or in which subtree we want to insert it. So since 8 is superior to 4, it means 8, the node with the value 8, which is this node here, will go into the right subtree of this tree here. So we look into the right of this, and then when we see any other node, we do the same thing again. We calculate, or we find out if that node has, if that node's value is less or superior to 8, right? So in this case, we compare 8 to 7. We know 8 is superior to 7, so meaning 8 will become the right child of this node here. So we'll do something like this and insert it at this point. And the same thing will happen with, let's say we want to insert a 0 in the tree, right? 0 is less than 4, so we'll traverse down the left side. So 0 is less than 4, 0 is less than 2, 0 is less than 1. So we are going through the left subtree, right, until we get to a point where the current node does not have a child, and we insert that node at that point. So 1 is superior to 0, right? So 0 becomes the left child of 1, right? Every value inferior to a node will become the left child of that node. So this is what we'll put here. So we'll put 0 at this point. So that's a quick recap on trees and nodes in a tree and how insertion of values happen in the tree. Now, coming back to our question, the question here is asking us to find a value in the tree, right? Let's find a value in the tree. Let's see if a value exists in the tree. If it doesn't exist in the tree, then we return null, right? So the value we are looking for is in this case is 2. So we are looking for 2. I'll put val here, val equals to 2. So how do we search in a tree? Now, searching in a tree is more faster than you would imagine because of how nodes are arranged in the tree. At first, if you do not know about trees, you would think it is complicated. At least that was the case for me when I was learning about trees. But in reality, it is actually simple and much faster. Now, why is it faster? It is faster because we know for sure in which direction, right, or in which subtrees the higher values are, and the lower values is in the other subtree. So, meaning if we have our value here, right, which is 2, when we get our value, which is 2 here, sorry, it is hidden under my face. So our value here is 2, right? Now we are searching for 2. All we need to do is to compare each time, right, in the tree as we are traveling down the tree. We'll compare the value to every node's value, depending on which direction we decide to head in. Now, if we decide to, if we decide to go in this direction in the left subtree, right? If we don't find that particular value in the left subtree, then it means the value does not exist in the tree at all. there is no way it will be on this side if we had already decided to go in this direction. We know for sure that in this direction we only have values less than the root, right? And in this direction we only have values superior to the root, so which makes this search a lot faster. If we get to a point, or if we get to a node in a tree, and that node value is superior or inferior to our value, the value we are searching for, we'll choose the direction in which we'll go into, right, based on the value of that node. So in this case, if we're looking for a value superior to 2, let's say we're looking for a 3, right, it means 3 is less than 4, so we'll go into the left subtree. Now when we encounter another node while traveling down the left subtree, we also need to calculate, we also need to compare the value of that node to our current, or to our target value, right, which is this value here. So when we find out that that value is superior to our current node value, then we know for sure the value will either exist in this place or it is not in the tree at all, right? So that is how the search will happen. So in this case, since we are looking for 2, right, our target here is 2. I'll put t is equal to 2. So 2 is less than the root node. We always start from the root node, right? So 2 is less than the root node, and we know for sure that means it is going to be somewhere down the left subtree. So I'll just stop at this point. It's going to be in this direction. There is no way the 2 will be in this direction here, because 2 is not superior to our root node, right? So since 2 is in this direction, we travel down the tree and search for it. So when we encounter any node, we find out if the value of that node is equal to our target. Otherwise, we decide in which direction we should search for that value, right? So in this case, when we are traversing the tree, we'll get to this point where the node's value is equal to 2. So we'll compare 2 to our target, right? So 2 will be compared to the target. 2 is equal to the target, obviously, and target is equal to 2. So meaning we found our node, right? We found this node and we return this node, right? Now returning this node, remember I said nodes have certain properties, right? Nodes have, values and right and left child, right? So if we return this node here, it means we are returning it along with all its children. Even if the children has other children as well, everything will be returned with it, right? So by virtue of the right and left properties of this node, we can simply return this node here and have access to every node down the tree, right? Every node that are children of this particular node here, in this case 2. So which is what the question is asking us to find, and the code for this will happen this way. So I'll go ahead and write the code once again. So let's use the playground to do this. Now here's what I will do. I will do this from scratch, not necessarily in the case of LeetCode. I'll implement the node class, and also implement inserting nodes in the tree, so that we also revisit those concepts as well. And also I'll also solve the question, which is finding a value in the tree. So first of all, we need to create a class called node, right, which is the node that we instantiate and insert into our tree. So we'll do it this way. We'll call this define. So create a constructor function. Now this will pass it a value, so I'll call this val, and we set this self dot value, or let's call this val. Okay, value is equal to val self dot right is equal to self dot left Yes, self dot left is equal to none. So right and left will be none at first, and then we'll create an instance. We'll create a class for our tree. So I'll call this bst, or let's call it bs3, right? And this will be like this. So we'll create a constructor function again. So this is what we instantiate the class with. And in the first, when we instantiate the class, right, we want to have a node, an initial node. In other words, we want to have the tree, the root of the tree. So we'll create a tree, a root property of this class. We'll set this to be none at first, and then let's define the insertion function. So insert node, I'll call this insert nodes. And now to insert a node, it means we want to insert the node alongside a value, right? So we create an instance of our node class. So I'll call this new node, and set this to be equal to the node class and pass its value. Now, first of all, we need to ensure that our tree has a root. If it doesn't, then we create a root for the tree. So we'll say if if um if self dot root is none, right? If the root is none, meaning there is no node in the tree initially, then we insert the new node as the root of our tree. So we'll say root self dot root self dot root should be equal to the new node, and then we terminate this here. So we return yes. So we just return and end this function here. Otherwise, if there is already a root node, then we need to traverse the tree, right, and determine where to insert the current new node. So I'll call this current node. Now current node will help us keep track of the node and reassign the next node to current node, right? So current node will be equal to self dot root, and we'll say while there is a current node, meaning while the current node is not none, right, then we need to determine where to insert this node. Now, sorry, here's what we need to do. Since we are inserting values in a tree, right, it is going to take a little bit of time to do that, right? So I will not say while current node per se. So what I will say is I will determine okay, let's create the current node. So I'll say current node is self.root. Then my loop will continue until I intentionally break it. Now the reason why I need to do this is because I wouldn't know when exactly I'll reach the end of the tree, right? In other words, I'll reach the right position to insert the node. So we'll say if the value, right, if val is less than current node current node current node dot value, right, if it is less than the current node dot value, then we have to insert it in the left subtree. Again, we also need to check if the current node is none, right, meaning if current node um, dot left is none, right, then we say current node, okay, current node dot left should be equal to our new node, and then we stop the iteration here, right? Otherwise, else we can just continue reassigning. So we say current node should be equal to current node dot left, current node dot left. And this thing, you have to do it a couple of times to actually understand it, right? To actually know the process or the steps you would take to insert the values in the tree. So somehow you probably need to memorize this, or if you don't memorize it, just practice this, you know, a couple of times until it sticks, right? So, which is why I'm even repeating it myself, because I want to practice it enough to understand and let it just become such second nature, right? So else, right? I won't say else directly. I'll just say, if so, else if elif elif val. Now the reason why I'm using else if instead of else is because in a tree we want to ensure that there are no duplicate nodes, right? So there can be two nodes with the same values in a tree. So we also need to ensure that if the value is superior to the current node dot value, right, then we insert this value on the right sub in the right subtree, right? um Current node dot val, then we say if current node dot right is none, then we say current node dot right should be equal to new node, and then we break. Otherwise, sorry, otherwise we do else current node should be equal to current node dot right. Okay, so this is all we need to do, right? And we insert the nodes in the tree. Now if you want to print the values in the tree, you can simply write a function. So let's write a function to say that as well. So we'll say, now printing the values in the tree is called traversing the tree, visiting every node in the tree. And there are a couple of ways we can do this. There is a pre-order traversal, which is something I only did once, and there is post-order traversal, both of them. And there is another one which is in order traversal. I've not done the last two, I've not studied on the last two, but I did pre-order traversal. So meaning, with pre-order traversal you visit all the nodes on the left in the left subtree before visiting every node in the right subtree, right? So it's also called a depth first search, DFS, which is another way of traveling nodes in a tree. So this we'll call this print nodes, right? I'll just define it like this: print nodes. And so this is a function, and you know what, I'll define this function outside so that we actually know what we are doing here. So this will be the root. The root will be an instance of the node, so let's assert a type on this. So it will be a node, right? And then all we need to do is to recursively call this function and add values um to the how do you call this, and add values to a stack, right? So we'll create an array, in other words, right? I'm using stack instead of arrays. You can call it arrays, you can call it a stack. I think I read that from somewhere, which is why the stack just stuck in my head, right? So let's put a result here. Now this result will be a list, right? So I'll call this a list. I think it's like this. Okay, sorry. How do you do this? I'm coming. I think I've forgotten. Um, Hold on. I'm looking for how to type the Wait, this result is a list, right? I'm trying to let me import the this class. So okay, I won't put a list of int. Okay, you know what? Let's put the list of ints here, right? Okay, this is how it's done. All right. So here's how the pre-order traversal works. So I'll call this, instead of print node, I'll call this pre-order traversal. Pre-order traversal. So if the current node is not none, right? So I call this root. Okay, let's just call it root. If there is a root node, right? So we simply say we call the pre-order traversal again, pass it the root dot left. So we traverse the left nodes first, and of course we need to pass in the results. So we'll say results here, and here's what we also need to do. We need to add those values to the results list. So results dot append, right, roots dot value, right. We traverse all left node, right, and then we do the same thing for the right node. So we say pre-order traversal or right subtree, sorry, roots dot right, and we pass in the result here. Okay, so what is this error here? Just want to be sure. More resolve. Oh, it's value instead of var. All right. Okay, that's good. We can do this to avoid that. I don't know why. I just sorry guys, my network is really bad today. Um, I keep going on and off. I hope you guys were listening while I was streaming. Um, hopefully my network doesn't disappoint me today, because when it goes completely off, I won't be able to continue the stream, which means it will end, right? So I'll try my best to um, go a bit faster so I can cover a lot of things today. Um, okay, so no, it's not your internet, it is my internet. My internet is actually bad, which is why the stream is being cut short. So um don't worry about it. It's on my end, it's my internet that is faulty. Okay, so let's continue, right? I'll close the chat now. And hi Dan. Dan is in the chat. EW is asking, what problem is this? I'm just you know implementing trees once again, and also I'm just implementing trees to solve a question. Yes. Yeah, I mean, it's just bad. The internet here is really crap. Anyways, so let's continue. So we create an instance of our binary tree. We'll put in some values here. I'll call this hey, this internet is going off again. Oh no. Okay. Let's put 10 and have okay, what's our question here? Our question is 4 to 137, right? I mean, we can arrange it in any order as long as we have 4 as our roots. So 4 will be here, and then we'll have 1, 2. I can put 7 here and 3 at the end, right? And you still see how the nodes will be inserted in the tree. So let's say for value in values, then we want to say value, okay, my tree dot insert nodes, we want to insert value in it. So now with this, the node class will be instantiated, and that node will be inserted in the tree. Now let's run this function and see if there is any errors. So there are some errors for us to solve. So node class has no val. So let's see where I did this. Okay, so I use value, right, instead of val. So let's correct that. So value like this. Let's run this again. Okay, you can see there are no errors, which means there is a chance that the nodes have been inserted in the tree. So let's do a pre-order traversal. I'll call this my results, which is going to be an array, and I'll say pre-order traversal, pass in my tree dot root, and then I'll pass in the results and print the results afterwards. So I'll just print results. Okay, so let's see what's here. Now you can see we have 4, 1, 2. Okay, because I have 1 in front, 1 will be inserted before 2. But if 2 was here, let's say I even had 1 at this point, right? 1 will come after 3. 3 will come before 7. So 1 will come before 3, sorry, and 3 will come before 7. Because 1 will be inserted on the left side of 2, right? 1 will be the left child of 2, and 3 will be the right child of 2. 7 will be the right child of 4. 2 will be the left child of 4 as well. So that is, an insertion and traversal of the tree. So let's see how we can find a value in the tree. So I'll write a function called so let's define a function here. I'll call this, so this is the function that will solve our question. So define find value, right? Find value. So we'll pass in a node or a root, and then we'll say this is going to be the node, and this is going to be result. So we don't need results actually. We just need the value we are looking for. So value is going to be an integer, right? So we are searching for a value in the tree. Now here's what we need to do. We need to take a copy. So I'll call this current node, just like the way we did before with current node here while we were inserting values in the tree, right? We use current node to keep track of the nodes we are visiting while traveling in the tree. So this is going to be equal to the root node, and then we'll say while current node. So since we are no longer inserting values in the tree, we are simply finding values down the tree. We don't need to use a loop like this, we just need to say while the current node has a value, right? We'll just do this. We'll say if the current node dot value is equal to the value we are searching for, right? We can just if it's equal to, we just return the node instead. So we'll just return current node, else. So if it's equal to this node, we just return the node. Then we search like this. We'll say if the current node dot value is superior to the value, then we will search in the left subtree. Is superior to value. Then we say current node dot current node should be equal to current node dot left, right? Because the value is less than the node value, so we need to look into the left tree. Else if current node, or we can just say else, right? Else current node should be equal to current node dot right. So we are going to look into the right side if the node value is superior to our current node. I mean, if the value is superior to our current node, it means there's a chance it will be on the left hand side. Otherwise, we just return none, right? Meaning we didn't find the node. So I will just say this should return okay, a node, right? So can you do node or none? Okay, this is possible. All right, that's nice. So let's see. We'll pass in a tree. So after traversing the tree, we can let me take this out, and then I will search for a value in the tree. So I'll say find value in my tree dot root, right? And I'm looking for the value 2, right? So this will return. So that we say I'll just call this ans, and I'll just say pre-order traversal of the ans, right? So pre-order traversal ans results. Okay, so let's see. We are not printing anything, so let's print results and see what we have here. Now you can see we have 2 alongside all its subtrees. I mean all its children nodes, right? So meaning, yeah, so this is how you print a tree, you add nodes in the tree, you find a value in the tree by simply traversing in a particular direction based on the value you are looking for. If the value is superior to the current node, it means you are going to look into the right subtree. Otherwise, if it's less than the current node, you are going to look into the left subtree. So I'll copy this code and put it in binary trees. I'll create a revision folder, or I'll call this repetition, and I'll create a basic file. So basics Okay, and let's place this here. So this is a revision of the basics on trees. So I'll just add this to my commit. So this commit, add git commit, git add, sorry, git commit dash m. We want trees, call this b st basics. Okay, so the next thing to do is to move on to the next question now, which is the question I started yesterday. So now the question we just solved actually will provide us, with some basic ideas to solve this question. So how do we solve this question then? Now, given the root node of a binary search tree and two integers low and high, return the sum of values of all nodes within a value in the inclusive range low and high. So we want to return, let me bring this here. Okay, I need to delete all of this. So this is done. Let's put this here. Now for this, we are given two range. We are given a range of values, right? A low and a high. So the low and high represent the boundaries for which we have to find the boundaries, yes, for which every node in this tree has to fall into before we add it to a sum that we calculate, right? So yes, I'm not sure if you get that, but I also don't know what I just said. So here's what the question is asking us to do. The question gave us a low and high, right, which is a range of numbers. So our low in this case will be 7 and 15. 7 and 15. So we are given 7 and 15. We want to find every node in this tree that fall into the range of 7 to 15. In other words, every node's value that fall in between 17 and 15. Now, the question also says inclusive, so we are including the borders of the range. So meaning the value of that node has to be either 7 or any value between 7 and 15 or 15 itself, right? So we want to have nodes that are equal to 7 or 15 or any value between 7 and 15. So in this case, when we begin to look at our tree, we can notice that 10 is between 7 and 15. So we add 10. So we want to sum all the values that fall or respect this condition here. So first of all, the value has to be either equal to 7 or 15 or any value between 7 and 15. So 10 is less than 15 but superior to 7, which means 10 is between 7 and 15. So we create a sum. We begin to calculate our sum. I'll say sum is equal to 10 plus, right? Now, we will do a traversal of the tree. We'll traverse the tree, right? And we know how to do a particular one way of traversing a tree, which is the pre-order traversal, traversing all the left subtree before traversing the right subtree. So we go here, we first of all go into the left hand side and we take the left node, right? Sorry. Okay. So we go into the left subtree, right? So when we are traversing this side, right, we'll first of all find this node here, and then we'll find out if this node fall into this range, right? So this node has a value 5, right? 5 is less than 7. So 5 is automatically not in the range of 7 and 15 inclusive. So we leave 5 and we search. So automatically, there is no need for us to go down the left subtree, right? We know every value on the left subtree of 5 will be less than 5. So we simply need to go on the right side of 5, which is 7. So we come here and we find, so this is 7. 7 is within this range. 7 is within the range of 7 and 15 inclusive. So we add 7 to this. Then once we are done with this, we go back to this place and we traverse the right subtree of the root. Once again, 15 is within this range, so we add 15 here. 18 is superior to 15, which means we would continue searching, right? We would continue searching after 18, because even in the case where we had maybe a value here, let's call this 14, right? We would have added 14 first before checking for 18, right? Before checking on this side. But we won't even need to check on this side, because 15 is already okay. We will need to check because 15 is exactly equal to 15, which is in this range here, which is the high value. And until we find a value that is actually less or superior to 15, we can continue the search. The value after 15 could be okay, any value after 15 will not fall into this range, even if it's 15.00. Okay, 0.0001. Okay, so meaning we end the iteration at this point, so we add 15 to. So at the end of the day, our sum will be calculated, which is 10 plus 7 plus 15, which is going to be equal to 17 plus 15, 32. All right, so this is our results, and as you can see, we need to traverse the tree from the root node. We need to do a pre-order traversal, and then after traversing, we compare the value of each node and decide if that node's value is going to go into our sum that will return at the end of the day. So let's see how we can do this. Now, I had already solved this, but I did not provide the solution here. Well, here's what I did yesterday, which is another mistake I made, and this is more of a lesson in Python than just data structures and algorithm. Now, I'm passing here. If you look at this, I created a pre-order traversal value, right? And I'm traversing the node in the tree recursively. I'm recursively calling this function. So this function will be called and will traverse the left subtree and the right subtree. Once we reach the end, we'll go back to the root and do the same for the root as well, right? Okay, so the problem with this is that with this implementation, what I'm trying to do is I'm just trying to pass in a sum that I will increase or increment every time I see a value that fall within the range, and recursively call the function again to find the next valid node value. So the problem with this is numbers are not mutable in Python, right? Numbers are not mutable, so you can't mutate a number. Instead, you can only change the value of a number, right? So meaning this total here will not return our actual total, because we are directly passing it here and hoping, okay, I am directly doing this, is my fault, so I'm incrementing num, which is not going to work the way I expected it to, right? So instead, here's what I was trying to do. Now remember how we traversed a list, right, with the pre-order traversal. Now you can see in this case we're passing a list, right? Result will be a list. What if we chose result as our, what if we use a list and then add in one one value into the list and increment that value anytime we see a node, right? A node that falls within this range. So here is what we need to do instead of passing some nodes as our, as an array, as an integer, we need to pass it as a list instead. So, or an array instead. So I'll say list here is going to be a list of integer. Come on. And then we import this, import here. Okay, so instead of doing it this way, we can just say list at this point here. So this is going to be the first list, right? Should be equal to node.value, right? So we increment this every time. All right. So and then instead of doing passing high like this, we'll pass high like this. Okay, so high also will be an array. So the array, the first value in the array will be equal to so here this is going to be some node 0, and instead of returning this, we can return the first value in the array like this. So here's what we need to do instead. We pass in a value, right? Hold on. So if some node is this, so we can set some node. Some node is a list. It's going to be an empty list, but an empty list value cannot be incremented at first, right? We can say, okay, we can do something like this. Yeah, we can increment the value, but then we need to set it first of all to 0, right? So sub node values, I'll say some node here, right? 0 should be equal to 0, and then we increment it here, right? Can increment it here, and then we return the first number in the array. Okay, so here's a bit of correction that I did today. Let me just show you how it is here. So range my summation, although this solution was really bad in terms of time complexity, or in terms of the rating on LeetCode, right? And recursively calling a function, I actually I didn't take my time to find out the time complexity of a recursion, but but let's see here. I can call this. Okay, so you can see. Oh, okay. So yeah, right. You can set some node to 0, or you can simply increment it at once. Okay, I did this, and you know what? I forgot. Because I was wondering, if there was no value in the array, how do we access the first value, right? Well, if we do 0 plus equal, it will automatically set it to the first value that it sees, right? So there's really no need for us to set that value before we start incrementing. These are like, things you learn along the way, right? These are things you learn. Even though you learn OOP, you might not know everything about OOP, right? Reference values and values copied by reference or by values, right? So in this case here, we are not really referencing, we are just taking that value, right, and mutating it. So we are mutating the value of the first value in the sum node array. So yeah, this is one of the solutions which is implemented using a a recursion, right? We'll look into recursion later, but like for now, this is what I did, at least an improved version of my solution from yesterday. And there is another one, right? A much better one, which has a higher time complexity, which has a higher runtime rating than compared to the other one, which was 19. Now, in this case, I'm still doing the same thing, but the recursion is only happening within the same function. In this case, I created a helper function from this class, um, which I don't know if it would have been different, you know, calling it from this function instead of creating another function in the solution class. But anyways, so here's what you it's still the same concept behind it, right? So if the node's value is superior or equal, I mean, if the node's value or root value is within this range, right, we simply take the sum and increment the value at that point. So sum will be instantiated to or created to 0 to be equal to 0, and then we'll recursively call this function, right, and increment the node's sum value each time, right? So each time we return node sum value, call this function again, and then we'll do this over and over again until we are done traversing the entire tree. So this is somewhat a pre-order traversal, and we are just, you know, changing the sum nodes value, right? Sum node value here is directly um, an integer. So we are using, so if the root value is 0, we return, if the root is none, we return 0. So node sum is going to be set to 0 at first, right? And then we begin to find the node sum. We begin to find out if the current node value or root value in this case is equal to or is within this range, low and high range, right? If it's in the range, then we increment the value of node sum. Otherwise, we check to see if the root value is superior to low, right? And then we look into the left subtree of the tree. Otherwise, we look for the value in the right subtree of the tree. Okay, so um that's it for this question. Let's move on to the next one. The next question will be on dun, dun, dun. Let's see, what question did I prefer for the next one? Okay, if I ever start studying DSA, should I start with the first lesson or just use your resources? I would say both, right? You don't necessarily have to watch the entire stream. You can just see, you can just skip through and see what is being done, and use the question or resources I provide in the description to study. Yeah, that's all I can say. So the next question would be this one: add two numbers. So this is a linked list question. It's LeetCode Medium, and let's see how we can solve this question. The reason why I chose this question is if you had solved this question before, there is a chance you can solve this. Where is the question? Merge two sorted lists, right? If you had solved this question before, there is a chance you would you would not struggle so much. You will struggle. There is there's an element of struggling in this question if you're seeing it for the first time and you're a beginner like me, right? You would struggle a bit to solve it, but you'd actually understand the concept behind it, and there is going to be, you know, a chance for you to solve it. So yeah, let's see what we can do with this question. So, like I said, this question is similar to merge two sorted list, and I'll show you why in a minute. But let's read the question. Now you are given two non-empty linked lists representing two non-negative integers. The digits are stored in reverse order, and each of their nodes contain a single digit. Add the two numbers and return the sum as linked lists. You may assume that two numbers do not contain any leading zero except 0 itself. So we have, here is our number, and we want to add the sum and create a linked list from the resulting sum that we made, right? So in this case, let's come here. I always forget to erase this board. Dun, dun, dun. Dun, 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 dun. Oh, you know what? I did not provide the code for the other solution. Okay, this is solution 1, solution 2. I'll provide it later and push it to GitHub for you guys to have access to it. Okay, so let's solve this question. This is a math problem, right? A math problem with linked lists. So we are given this list and this other list here. So two lists, and we want to add the values in the list, right? We want to add them to return a resulting list. So we'll have something like this. So we'll have 2, 4, 3, and 6. Sorry, 2, 4, 3, and then 5, 6, 7. So let's say we have 2, 4, 3, 243 plus 5, 6, 4, right? Now the addition is done in reverse order, right? It was stated in the question. So okay, where is this? Merge two sorted is add two numbers. Okay, so the addition is done in reverse order, right? The digits are stored in reverse order, meaning we are adding from right to left instead of left to right. Normally we would have done, this. We'll say this is going to be equal to 7. So we start our addition here and we go down. But in this case, we want to start the addition from this point all the way here. The reason why we are starting the addition in this form is because we access the inputs are a linked list, like, right? And to add values in a linked list, we have to add values from an array, right? We iterate through an array and add those values into the list. We instantiate a node class and add the values in the array as the node's value and then insert it in the list. So meaning we start from this point all the way to this point here, which is at index 2. So 0, 1, and 2. So at this point, this will be our last value in the array, which is why the question says it's in reverse order. So we do 7. So 2 plus 5 is 7. Now 7, we get to this where this is 10. So we don't write the entire 10. So we write 0 and then we'll retain 1, right? We'll retain 1, or we'll carry 1 to the side, and then we'll add 3 to to 4, which is 7, 7 plus 1, which is 8. So our resulting linked list would look like this: 7, 0, and 8. So this is the version of, the resulting linked list will return at the end of the day. So how do we do this? Well, we know to access values in a node, in a tree. Oh God, I keep saying tree. To access values in a linked list, right, we need to traverse the linked list from the head node all the way to the tail node. And in this case, we have to do that simultaneously. So in each case, we'll sum the values of the nodes, right, in every iteration until we reach the last node in the linked list, right, in both linked lists. Now, in some cases, we might not reach the last node at the same time. A list might be shorter than the corresponding list, so we just need to handle that edge case at the end of the day. But the main idea is to actually understand how we carry out the addition of the values will be done with a little bit of care, due to the fact that we have to carry values and then add them to the next sum, right? So here's what we need to do. First of all, we take we traverse the node simultaneously. We start with the head node and the head node of this node, right? And then we find the sum of these two. Now the sum of these two is simply going to be 7, right? We don't need any carryovers here. We don't need to retain any value at this point. 7, and then when we set this to the next node here, we set it to the next node, we move to the next node. Now on the next node we have 4 and 6, so we add 4 to 6. This will be equal to 10. Now we can add a node with the value 10. That would have been nice and easy, but we need to be careful of what values we store in a node, especially when it's a 2-digit value. We need to retain some values and add others later on. So then we'll need a way to retain this value, right, and then adding them later on. So if you look at this very well, you can see that we wrote 0, we stored 0 and took away 1, right? Now storing 0 means we are probably doing a division here, right? So if we divide this value, here, if we divide this value by 10, right, we'll have 1. So meaning we are carrying away a division of the value by 10. And we can say the resulting value minus this, because this will give us 9. So the value we retain here, or the value we stored as the value of our node, will be calculated as the remainder of a division by 10 as well. So if we divide this by 10, we'll have 1, right? 1 times 10 is 10, so 10 minus 10 will be equal to 0, right? So there's no remainder for this, so we can use the modulo operator to find the remainder of this value, and that remainder is what we store as the value of the node at that point. So we'll have to pass to the code and see how we can solve this. So I'll come here, I'll copy this part because I need it. This will be a linked list problem. I'd read Oh, it's already 9 p.m. Wow. Mm-mm. This is going to be this. It's code number 2. I think it's number 2, right? Yeah, add 2 numbers. So I'll put this here. Take these parts away. Okay. This here. Remove this. I will take this part and so let's begin. Right, we need to traverse the list at the same time, and also we need to create the resulting node we want to return. Right, so I'll call this. Usually we call it dummy node. Uh, I'll say this is going to be dummy node. Dummy node is going to be equal to node. Okay, let's just call it. I'll call it result node. You know what? Dummy is short. Okay, okay. I'll call it results node or new node. Yeah, let's call it new node. New node is going to be equal to a node with the value 0. Now, the reason why I'm doing this is because at the end of the day, I want to return a new list, right? So now I'll create a variable for the values we are carrying out or we are retaining. So I'll call this retained. This will be equal to 0 at first. Now the next thing we need is to take a copy of this node so that we can do current node.next, current node.next. So say current node is going to be equal to this new node. Is going to be equal to this new node, right? Yeah. So we can say if so okay, not if, we can say while we have this node L1 or L2, we want to keep traversing the node or even the retained, right? When there is a retained value, because there can be a retained value that we will need to add somewhere where there is no addition of values, right? So let's say while these two, we can say I'll call this value 1, which is going to be the value of the first list. I'll say return L1 the value if L1 else return 0, right? And then value 2 will be equal to L1 dot L2 dot value 2 if L2 else return 0. Then we can say our we'll say retained retained is going to be equal to um is going to be the division of the total, right? So we'll say value 1 plus value 2. I'll call this total. Total is going to be equal to val 1 plus val 2, and I'll say total divided by 10. Now if I do this division like this, it will return decimal places, so let's make sure that it is rounded to the nearest zero value, right? And then we'll say new node is going to be equal to the list node. Okay, is it list node? Okay, list node. We can pass it the total, but we don't want the total directly. We want the total, the remainder of the division by 10, right? And then we say current node dot next should be equal to the new node, and current node, right, should be equal to the current node dot next. Okay, and with this we are okay. So let's see, what are we returning at the end of the day? We can return, so this is not the final code, but let's just test something out. So we can return new node dot next, because at the head it will have 0, which is not what we want, right? New node dot next, and yeah, so let's do that first and we'll test it out and see how it works. Dun, 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 dun. Okay, at least it will work for this case, and it will work for this case, because this place we have equal number of nodes in both lists. So I'm just trying to see, hoping it works. Okay, so there is an issue. We are running into an infinite loop, and we need to catch some infinite loop here. So timeout, timeout, timeout. Now one thing I'm not doing here is moving on to the next node, right? So we'll say, after finding out this, we can say L1 should be equal to L1 dot next. So L1 should be equal to L1 dot next, and then L2 should be equal to L2 dot next. Okay, so let's see how this goes. All right, so let me do it here instead. What does it say? What is first say? Non-type has no attribute next. Interesting. Interesting. Dun 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 dun. At least, I mean, if it fails, congratulations. The best dancer, yeah. Yeah, it means this was shorter than this, right? So let's see. dun, 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 dun. Okay, I must have made a mistake. File dot next. I just want to use one test case, right? Can I do that first? Okay, let's see if this will work. Okay, now this is working, but there is a wrong answer. Okay, so we want 7 plus this. The new node is this, right? So current node, which is this head node, dot next is the new node, and then current node becomes current node dot next, which is the new value we added here. So why is this not can be started. Okay, so okay, so here's my mistake. I'm just adding the nodes without adding the retained value. Okay, this should work now. Hopefully it works. Oh, what went wrong now? If we divide 10 by 10, right, we have 1. So we retained 1. And then we add 1 in the next calculation. So, what's your problem now? Let me see. Let me bring this back. Must on the beat. So we move on to the next node. The next node. If next node of value, else we return 0. Here we create a new list node with this value. Current node is equal to new node. Okay, you can see this is bad. I'll say you see, this is my problem here. Dummy node. You know what? I'll end up calling this a dummy node. Dummy node here. Okay, I hate this cursor. Current node. Yeah. So let's see where we go with this. My friend. One more time. Before. Alright, let's see. This should work. Oh no. What? Hey, okay, I'm still using. Okay, new node. I'm still returning new node dot next. I want to return dummy underscore node dot next. So we say dummy node, return dummy node dot next. Exactly. Aha. Now this test case worked because the values of the nodes are equal, right? So which is why I had to use only one test case, right? We can use we can when we test with other test case where we have unequal values of nodes in each list, then we'll end up with a node that has more values than the other, right? So here's what we need to do. In that case, right? In that case, we'll just add the edge case for that. I'll bring this here, and then I know this took a little bit of time, but it's good to make mistakes. Oh god, it's good to make mistakes too, you know. Now, the reason why I said this question is similar to this is because of the the edge cases at the end of the day. You can see we check if list one is not none, then we add the remaining values of list one to the node, right? So do the same thing here. So if L1, if there is L1, right, I'll just put if L1, then um we'll just do current node, sorry, we'll just do the dummy node. No, we still use current node, right, dot the next should be equal to, did we use current node here? Oh yeah, we did not use current node, we use um yeah, we use current node. Okay, we use current node, and then we return the placeholder. So we'll do the same thing here. Current node dot next will be L1. So L1 dot we are going to do L1 dot value, right? Else, do we even need this? I just did this because I thought it will work. You know what? Let me let me try this out first. Uh, I'll copy this part of the code. I want my test cases back. How do I get them back? Yep, and yep, and yep. Oh, wait. You can have as many as you want. Really? Oh, no, no, no. This just duplicates everything. Punk. Let's refresh this and see if the test cases will be back. Okay. Okay, the test cases are back. So, oh, you can write your own test cases. Okay, interesting. Let's see what will happen here. I doubt this won't work, but oh, wait. Yeah, you see, this was the error I was talking about of unequal nodes. Okay, okay, okay. That's fair enough. Um, what if we just say this if L2 dot next else just, and then we'll do the same thing here. If L1 dot next else none as well. I'm late. My time is totally up. Uh, okay. Let's check the chat and see. Yes, he has no attribute next, so just none. It's if he doesn't have a next attribute, then don't know, don't know, don't know, don't know, don't know, don't know. You know what, guys? I've solved some questions for you, so um, I need to go. My time is up. I've done more than I should today. Uh, let's push this first, and I will provide the solution after the stream. I'll research more. This git push origin main. Let's check if there are any questions in the chat. Um, you got up at 5:30. That's nice. Um, by the way, why don't you use ChatGPT? Oh yeah, I occasionally use ChatGPT. It's not like I don't use ChatGPT at all. I use ChatGPT when I'm studying, right? So meaning I try to solve a question first, and then when I'm completely stuck, then I'll go to ChatGPT to let ChatGPT explain the question. Then I go back to solve it again. This thing take like an hour plus, which is why I don't do it on the stream, right? So yeah, understanding the question and knowing algorithms and so on takes time. So which is why I don't do it on the stream. Okay, guys. We continue tomorrow. I will try again. Tomorrow is another day to try. Yeah. Stay coding. Um, have I started dynamic programming? No, I haven't. I have not started dynamic programming at all. So, 100 days to study data structures and algorithm is not really to master data structure and algorithm in 100 days. That is impossible, right? So, it's just to cover certain things and just get familiar with the whole idea of data structures and algorithm. And then after 100 days, there is now a much more practical part to it, right? So you now know your way around things, you know what to do next, you know what to study, and it's sort of a way to find a roadmap for yourself, right? Which is what I'm doing now, and I'm also sharing my journey with you guys. Okay, so one day I will start dynamic programming, and I am not sure if it's going to be within this 100 days, which I highly doubt. But I'll still keep posting content here, um, even after finishing the 100-day streams. Okay, bye, guys. All right, bye, EW, bye, Ransom, and bye, everybody in the chats, bye, everybody on the stream. Stay coding, keep practicing.